Hello, everyone. Good evening and good day to everyone from all over the world. Welcome again to another day, another session for on this World Corrosion Awareness Day. Thank you all so much for joining us again for the past few days. That's been really nice. Straight onto our program. Brief overview of our housekeeping. This session was a technical presentation to be delivered by our speakers, and after which we'll have a question and answer segment. Participants are encouraged to take note of the questions during the presentation and share them during the Q&A session. Kindly drop your questions in the chat box as the session progresses, and they will be attended to. Recording notice, please note that this session is being recorded for documentation and knowledge sharing purposes. And by participating, you consent to the recording, which may be shared within the AMP community and used for future reference. Also, all attendees will get a certificate of attendance, which you can use for your professional development hours. Before we go into the session proper, we have just a brief introduction on the presenter today. Um, his name is Engineer Agapi Ushula. We have a brief, please stand by to a brief.
With over 15 years of deep expertise in corrosion management, fixed equipment integrity assessment, and technology implementation across the African energy sector. Agape Osula is a highly proficient corrosion and asset integrity professional with over 15 years of deep expertise in corrosion management, fixed equipment integrity assessment, and technology implementation across the African energy sector. Based in Lagos, Nigeria, he is recognition as an AMP certified trainer and holds NACE international certifications, including Senior Internal Corrosion Management Solution called the No Leak AIM solution. He has played active leadership roles within both NACE, pre-AMP, and AMP organization, contributing to their professional communities. His commitment has been previously recognized with NACE International's Leadership Award. Furthermore, Agape founded the No Leak campaign to promote asset integrity awareness across the region. Please join us in welcoming Agape Osula, whose dedication and expertise continue to drive improvements in the asset integrity industry.
Okay, good evening, everybody. I guess I can start, Mr. Samuel.
Yes, please.
Hello. Can you hear me? Can everybody hear me?
Yes, we can hear you, please.
Hello. Is it good? Can everybody hear me? Yes. Okay. Good. So, good evening, everybody. My name is Agape. Okay, so I'll just talk a little bit around the topic, which I'm to share about, and I think we can discuss. So it's not. I'm not doing a lot of deep dive. I want to have a conversation as much as possible, and then we can share ideas and also look at what is currently happening in industry now for Cathodic Protection Management, and also what the future entails. Okay, so just to give a brief overview of how external corrosion management of general corrosion cell as you know, we have the cathode anode electronic part and the electrolyte. So generally speaking, the way corrosion occurs is that on the anodic side it corrodes, and then the cathodic side kind of helps it continue to corrode, right, by providing the potential difference, and then also it's protected on cathodic side. And then you have rust and what, and of course you need an electrolyte and electronic part for electrical connectivity. Okay, can everybody hear me? Just so I know that I'm not speaking to myself. Yes, okay, that's good. Okay, so generally, for pipeline systems, we have two general types of protection. We have the impressed current and the sacrificial anode, and sacrificial system or galvanic system. So principally, the concept of galvanic system is just create the same corrosion cell which already generally exists, but just make sure that the one which is corroding is the one you don't want to corrode. So we have using things like active magnesium, aluminum, and zinc and the likes as anodes. So all we just do for galvanic cells is just to connect another anode to what we want to protect, and then let the anode corrode. So just the same concept of protection, and just is what we use for the galvanic cell or sacrificial system rather. Of course, on the impressed current system, it's a little bit different. For that, we send in current to charge up the material itself to a region where it cannot corrode. So over the years, we already know that the corrosion is an electrochemical process. So all we decided to do as professionals over the years was, okay, it's an electrochemical process. Use the same electricity to make sure that it doesn't corrode. And then investigation have been done over the years to find the potentials in which every material will be at particular soil for it not to corrode. So what we do with impressed current systems is that we just send current into the system and take the potentials to that region so that it doesn't corrode. So this is a very important topic, because we know that once we maintain equipment at those potentials or those voltages, they will not corrode, and if they don't corrode, we are able to protect the equipment for a longer period of use and the likes. Okay, so these have been done over the years. We know monitoring criteria from this SP0169, which is the -850 millivolts, IO3 instant off potential, and of course the 100 millivolt polarization shift. So we've done this over the years. We already have good understanding about how this works. So generally, we are as a rule of thumb, the industry is generally comfortable with protecting materials at these voltages or potentials, like we call them. Of course, we have special considerations for microbiologically induced corrosion environment, where we need to take it a little bit to -950. Further than the -850, which is general, and of course with high temperature regions, where we also take it further. Of course, IO drop corrections for multi environments where the IO drop is undulating and the likes. So we know these are generally industry standards that have been accepted over the years. So these are not typically the problem. Now, what tends to happen right now is that sometimes after implementing the system, we have to generally monitor, check, are we meeting these standards? Are we meeting these criteria? So we can be able to so can be rest assured that we are protecting the system. So one of the processes in which we check is what we call the closed interval potential surveys, right? What we just do in this process is that that we try to measure the potential of the line along the right of way from the beginning to the end. What we're trying to do, we're trying to make sure that we keep the potential which we intend to achieve, the entire line is in that region. And then when we see that there's a particular location where we don't have those, where we are not able to meet that criteria, then we begin to investigate and we begin to fix, or we try to fix. So this has been done over the years. like I said, the industry is already aware of this process, and everybody industry-wise is comfortable with the implementation for this particular methodology. There have not been, while sometimes there are one or two conversations around why the potentials of 850 is used. While there are variations, generally we already agree, that these potentials are okay. So what happens in the industry is that we do close interval potential surveys. We see the potentials. If there's a need for adjustment, we adjust the transformer rectifier unit. If there's a need to scale down or increase, we increase. There's a need to scale down, we scale down, and this has been going on over the years, right? Now, where the issue tends to come sometimes is the frequency at which the closed interval potential survey is done. For example, you could be doing it routinely, but be doing it at a time when you cannot detect anomalies. Now, remember, the idea for protection is that we want to have protection over the years. So we've seen people, or we've seen equipment which are under CP protection. However, after a while, they will fail. Then the question becomes, how come? What's happening, right? Various things, of course, will contribute to it, right? But we know that if you keep it at the right potentials, if you do your continuous monitoring, that scenario will not happen. So this is where technology comes in. This is where innovation has stepped in to help the industry to grow in that light. Like I mentioned, the closed interval potential survey, all it involves is just the same general potential measurement on the pipeline along the right of way from beginning to the end. So we synchronize, we do a current interruption, because we're trying to monitor the on and the off potential. We do a current interruption, and then we just put the trailing wire on the test post, and then we monitor potentials as we walk along the right of way. Okay, so I mean, with this we can discover anomalies, right? We can see where there are issues. We can begin to say, okay, based on these issues, what should we do, right? And then we can make repairs where that is. Now, of course, because this CIPS survey is a manual process, there are blind spots. And then one of some of the blind spots is that if you have under or over protection at the periods when you are not doing your CIPS survey, you will not know. And this is very, very important, because we want to maintain the pipeline at those potentials throughout the year, not at certain times, right? Now, if maybe, for example, you do your measurement at specific times, which is maybe some people say every 6 months. I mean, sorry, some I think in Nigeria the law says every 2 years. Some people do it every year. If you follow those schedules and then you do it at periods when a certain period, you may not know what's happening in other periods when you are not doing it. And that is where technology has to come to help. Because what we do now, what operators are interested in now is precision engineering. No more too much of lapses with regards allowing things fly, right? So this is one of the blind spots of CIPS survey. Sometimes some companies do it for every 2 years. Some companies do it every 3 years. Some companies do it every year. But anyhow you scatter it, there are going to be periods where you don't know what is happening on your pipeline, and this is very, very important. Now, sometimes you also have TROU downtime, right? For example, and this is of course very this is very popular in Nigeria. I would say there are specific issues that could happen, right? That could take your TROE out of service. Now, if you are going to depend on your next CIPS survey to know that TROE is not delivering current to your system, and this particularly for impressed current systems, right? If you are going to wait till that time, then that means, if, for example, if you're doing this every 2 years, if you're going to wait till that time, that means for the next 2 years, you will not know that something is happening on that line. And then when you come again after the next CIPS survey, and then you see that, then you cannot begin to do tuning. That means that for a significant period of time, something will happen to your TROU and you were not aware. Now, some people say, okay, we do monitoring. We go to look at the TROU every 3 months, for TROU inspection and the like. So your electrical team can do that. That's important. But if you do it every 3 months, perhaps I think the only alternative is to make sure that you are precise in this TROU downtime. So do it every day, right? So that at least when your TROU is down, you know instantly, and then you implement remedial actions. So this is also one of the drawback of doing this manual method. Okay. Now, of course, we have cable and anode failure. This happens a lot in Nigeria because we have lots of vandalism and the likes. Sometimes also you have encroachment by foreign actors into your pipeline and the likes, right? If you wait for your next manual inspection, you will not know, and then you have a period of unprotection, so this is where, of course, technology comes into play to try to help. Of course, one of the interesting parts is, of course, coating degradation. So this is perhaps very important for CP professionals, and I speak a lot about this to a lot of CP professionals. The concept of understanding why your current demand increases, particularly when you are running your CP system on constant potential, is very important, right? So you should know, okay, my current demand, what is happening? I mean, with that, you can plot your anode life. You can do a lot of analysis on your CP system. For each CP system, is the coating degrading? Why is the current demand increasing? What's happening? Is it environmental factors? Is it temperature? Is it things like that? So with that, you can have a complete understanding of what's happening in your system. And there are some systems where that are running on constant voltage or constant current. Also, this is also very important, right? With this, you can know what's happening. If you're running on constant voltage, when your current demand is adjusting, you can also see what's happening, and then you can make deductive to say, okay, are we having more coating degradation, or is it something else? So this is quite very important. Of course, you have the AC interference. Of course, when you're having this current from nearby, you would only know when you come to do your next survey. Of course, compliance gaps. Some people take, like I said, do quarterly for limited potential measurement, and then for CIPS they do long 2 years and the likes. Yeah. So, of course, these community issues are, of course, most, like I mentioned initially, they are more peculiar to Nigerian environment. We have a lot of community encroachment and issues. So this is perhaps the reason why lots of people are shifting from manual CP inspection to technology. Now, this is just like a general overview, right, of how the CP remote technology works. Okay, so generally what happens is we have a feed equipment, right, which is installed on your TROU or on your test post, right? What it does is it's an IoT device, and what it does is it measures voltage, right? It measures voltages across or your electrical data and sends to your system. So with this, going through the pipeline may not be necessary anymore. Reference electrodes, of course, are installed permanently. You have shunt sensors which track. They all help to track pipe and soil potentials continuously. And of course, you have coupons also, which also help a lot. CP coupons are actually very, 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 very important. And I think it's very good to mention this. They help a lot, particularly when you are looking at interference issues. They help a great deal. So when you are looking at interference issues, use of CP coupons are very, very important to understand how protected your lines are, particularly when there are DC interference issues. Okay, so of course, data transmission. So they transfer from the location to your system. Of course, the data feeds encrypted. Some device, some systems of this CP remote monitoring, they schedule the transfer, right? And they could hold the data for a particular period of time in their data in their localized database, and then they send everything once to the database after a certain period. Why some just keep sending continuously? This significantly. So imagine a system which takes data from your CP system every second or every 3 seconds, or every 5 seconds, or things like that, compared to a system where you have to do it every 2 years, or even if you are doing it every 3 months. You know, this is better. It's more efficient, and it's of course it closes a lot of the gaps. You know, so you can take faster decisions. Of course, your monitoring centers, generally you have like a cloud-based system which receives all the data, and then has interpretation, it does trend analysis and things like that, so you can be able to interpret what's happening on your line. Okay, so like we mentioned, like the benefits of using this system is that, of course, it reduces costs, it cuts your security concerns significantly. This is very important for places like West Africa and Nigeria, where you have like a lot of security issues when you go for a right-of-way survey and CP inspection on the field. Of course, it minimizes field deployment and data collection. It shifts from reactive repairs to predictive maintenance. So this is very important. Currently, systems which are manual are more reactive. So, for example, you wait for a while to do your next inspection, maybe in the next 2 years, before you know something is happening in your line, right? With these ones, you can trend and know, okay, what's happening per time, and then you can be proactive to say, okay, with what I'm seeing certain things happening, and then you can take actions, you know. Of course, / logistics and community costs and the likes, which is of course very popular to if you're in Africa. Okay, of course, safety and compliance. We have to 24/7 monitoring. You eliminate crew exposure to hazardous or remote locations. Very important. Tamper-proof records are very clear, integrity-wise. You can do integrity audits. You know exactly what's happening in your line, and then you can take actions as quickly as possible. Very important also is that you have measurable lower carbon footprints from reduced travel. This is also very important. Okay, so of course, enhanced performance, round the clock visibility, you know what's happening. You can detect 14 hours, not months or years between inspections. You have data-driven rectifier outputs, and you can do CP optimization. CP optimization is very important because if you see, for example, you have maybe there are certain periods within the year where you have drier environment and temperatures are better, and then you see your potentials going out of protection range to overprotection range, you can automatically tune your TRU or take action on your TRU to reduce current, right? And then if the reverse happen, maybe you have like scenarios where maybe there's temperatures are down and you have more current demand, and it's not, maybe you have tuned it to a particular setting, you can perform an adjustment and know what is happening instantly. So with this, you have like clear, precise monitoring of your system. Okay, so the components generally for your remote monitoring system, it's you have your remote monitoring units, which you install on your rectifiers, your test stations, on your bond junctions. You install them on to capture voltage, current. You set them also on your on the test post along the right of way, right? They capture current, voltage, they can capture temperature, they can capture a lot of other things, right? And then of course majority of them are battery operated, so because they have to be powered. And then of course you have sensors and electrodes, like your permanent surface electrode, which is installed. You have shunts, you have lots of coupons and the likes for interference, for monitoring interference, and of course corrosion rates and the likes. So of course, like I said, power is mostly battery. If you have a solar system, you could use, but most times we generally advise that you use battery powered, and of course cellular or Wi-Fi compatibility for depending on the environment where it is located. Generally, you have rectifier monitoring, right? You will see your DC voltage, you see your DC current via precision metering shunts. You can see any AC supplier issue presence you have. You can see breaker status. You can see, of course, like I mentioned, you can see temperature, operating conditions, and the environment where it is located. So, for example, if you have a pipeline that is running through a very long distance, right, it would be safe to say, okay, you don't assume your temperature at the entry point is the same as a temperature as you move along the right of way, right? So with this, you can have like a good understanding of what's. So if you have more current at a particular location, and you can look at the temperature and say, oh, okay, it's because of temperature changes. You can make those intuitive justifications and understand what is happening, and also be able to predict what will happen as time goes on. So this is quite very important for for professionals who are very, very interested in following up on processing and what is happening. Okay, so yeah, of course, of your test station, your test posts and your pipeline, of course, you can measure. And you can measure pipe potentials. You can measure your instant off. Your AC/DC coupon densities. You can measure bond current readings. Very important if you have neighboring structures and you have bonded your pipeline to other pipelines and the likes. You can measure stray currents, AC interference mapping along the right of way. You can do your coating health indicators. You can do. So, for example, so this photo just generally shows for our own system how our devices relays the data. Right, you could see, so you see TP pipeline 001A, the location which the KP is located in, this particular measuring IoT device, the description of the location, if it's upstream, a flange, and things like that, and then you can see the dates and the readings that's collected for a period of time, and then you can see. So if it were our system, you would just see that these values will be changing routinely, and then you can have a history to know what is happening. Right, and then if maybe they are locations which are unprotected, you can see them, right, and then you can also have a history of what's happening and say, okay, what's happening at this particular location, right, compared to this location, what is happening? Are we having interference issues? Are we having like is it like before the CP system gets here, the current has dampened, and like, so you can make very important decisions based on the data you are getting from the site, and then you can know how to adjust. For example, although minus 850 is not so bad, but imagine a situation where your CP system is not able to protect the entire length of the line, right? With this method, technology, you can be able to tell, okay, what's happening across the entire line, So, of course, communication, like we mentioned initially, they are mostly cellular. Of course, sometimes they could use Ethernet cables. You could use fiber optics, satellites, and the likes. All the systems tend to ensure that you have data protection, which is very important, so nobody gets to get the information about how the data you're getting from your field is collected. And of course, you have data analysis platforms. For this, just for some of ours, our own, where we have like where you can see for your entire line what's happening, protection levels, conditions and the likes, and then you can make judgments or intuitive judgments without going to the line, or you could make judgments which when you go to the line, to the system, you just make your changes and then leave. So it's easier. So you don't need to go through the entire right of way, right? You can just, from your office or from wherever you are, you can make those judgments. This is what technology is helping us achieve, right? Of course, there are field apps. Sometimes you can have them on the iOS, Android apps, and the likes in the feed, for which you can look at and you can monitor. So just a little bit of a small system where this was done in Middle East. We installed a CP remote monitoring system on the chalk line, right? And we piloted it for one particular pipeline, and with this, we're able to see what's happening across the entire in the line at different sections of the pipeline and the likes, and then we can see, okay, where's protected, where's overprotected, where's underprotected, and then we could see. This was very important because they for this particular system they were having a lot of interference issues. And this one was actually interesting because the interference issue was not from external pipeline, was from their own system. So they have multiple systems, multiple lines running through different locations, other different CP systems, all having interference, right, amongst themselves. So this helped them a lot. And also when they had like a CP transformer fault, they detected it easily. It was easy to detect because you had systems which could instantly send you readings, and then you could see what's happening, and then you can also know when the issue started. And this is also very important. You know, in the last system which is manual, you will not know when the system started, right? You will know, okay, when you go for your next inspection, maybe in the next 2 years, if you are doing CIPS, you see, okay, we have an issue in this particular location, right? But when it started, you don't know. You understand? But with these systems, you can know, you can measure. Technology has come to make life really, really easy. You can make deductive, what's called findings, do checks, do query data, right, to see what's happening. And then when you implement changes, you can also monitor to know how effective the changes you have implemented, how is it performing on the field. Of course, in our implementation, what we have to, of course, we have to assess the site for power supply and communication coverage, implemented, match our RMU sensor layout and the likes. We prioritize, of course, high consequence areas. So what this means is that there were certain locations which were going through certain places which were populated zones, right? So we had to do install extra test posts and the likes for more effective monitoring, and then we mapped the entire environment. For example, if you look at ASME, I think it's the ASME beta. I think it's DNV. I think it's F101. If you look at it, it's categorizing safety factor based on the number of people in the region where the pipeline is passing through. So it specifically says that you should map your lines into different regions depending on population and impact when it fails, when something happens to the line, you know. So this is very, very important. I think it's also in B31.8 ASME, right? This is very important, so that because criticality, a pipeline which fails at the location where there are no people, the criticality is different from a pipeline which fails the location where there are people, right? Because the consequence is different, you know. So with this, you can map, and then you can know, okay, which region are more critical, they are less critical, and then you can monitor those regions also more effectively without waiting for the next 3 or 5 years and the likes. Of course, you can set your alarm thresholds, 850, 950, depending on your protection criteria, depending on the environment which you are transversing through. Yeah. So our deployment were mostly like, of course, source protected RMUs. We established equipment data, define calibration intervals for the electrodes and the lights, and of course feed sensors, and of course train operations on dashboard manipulation. Right. So the future for CP monitoring for me, what I see is predictive analysis, right? Generally, currently, we have machine learning models which can determine corrosion rate, the corrosion rate from potential measurements. Okay, what do I mean? If you have, we know that corrosion is an electrochemical process, right? Now, we also know that we can calibrate what the corrosion rate will be depending on the potentials we are measuring. This is general data we are already aware of. Now, we have all this information. What we don't have is data interpretation, right? How much can the human mind interpret of all the information which we are gathering per time from our assets? Like I always say, the oil and gas industry doesn't have a information availability challenge. We mostly have a data interpretation challenge. So we have too many data and too few people looking at them. right? So most people are not looking at the data to make deductive deductive information, rather to make deductive process to deduct what to do next, generally speaking, right? So that's where machine learning models come into place. From us at GKS, of course, we've developed some machine learning models for things like this, but of course, knowledge in the industry, knowledge is fueling into this continuously, right? To develop, okay, how can we be more precise? The idea of having safety factor very high is not it anymore. Right now, we're looking for what's the closest margin we can use to operate the facility at minimum costs to have maximum output. So this is where machine learning models come in. Machine learning models are being developed every day. We are contributing to the industry, and other parts contribute to the industry. For example, some of our systems currently, we are measuring the corrosion potential of specific materials in specific environments based on the potential measurements, corrosion rate rather, based on the potential measurements, right? We're doing lots of this analysis, and I know a lot of people are also doing this analysis and putting data out, and that's where models will come to help us make integrity management better efficient, better precise, and of course more impactful. Of course, they are an automatic anomaly detection. Currently in our systems, even the system generally would prompt you when you have over protection or under protection. But when we are moving towards, I think, like I said, the future of CP monitoring is the system, when it sees these anomalies, can auto correct itself. For example, we have something already similar for CP systems where they are using constant potential monitoring, right? So for those systems, normally the TRU keeps changing the potentials based on what it is measuring from the reference electrode. However, for those systems currently, the reference electrode for the TRU is the one close to the TRU system. It's not the ones along the pipeline, right? So if it detects perhaps a potential which is beyond a particular level, based on one particular one, it can make deductive changes. But where we are going to, right, is that across the entire network, right, it's taking potentials across the entire network, and based on all those potentials, it's making deductive reasoning, deductive changes. For example, we know when we send current from a particular location at the entry point, as current goes along the pipeline, it dissipates, right? We have leakage, we have a resistance along the pipeline, and then we have a current leakage as we go along through the coating holidays, right? Now, where we are going to is that your CP system will take potentials across the entire location, across the entire right of way from the beginning to the end, and based on that, adjust TRU. When I say TRU, that's a transformer rectifier current delivery, to make sure that across the entire network, everything is protected. And that's where we are going to. So we have pattern-driven interventions. So we'll not just only to tell alarm, okay, based on one location, it is bad. No, it's across the entire network from beginning to the end. Particularly if you are protecting your pipeline from only one TRU on one side. You understand? So this is perhaps very, very important. And of course, you have the self-improving algorithm, Sharpen, of course, which improves itself, data accuracy, and the likes. We'll have automatic adjustments for current and voltage, which I was talking about, to meet potential criteria, but just not for just one particular location, for the entire line network from beginning to the end. Of course, the IoT sensor networks, meter level pipeline coverage, granular corrosion mapping. This is very important. For example, if you have protection at the beginning, and then as you go along the line, you don't have protection, and then you have protection at the end, the question is what's happening at the middle section of the line, right? Are we having interference issues? Are we having is it that the other end of the line is protected by something else? Not necessarily CP coins, which are set from the beginning of the line when you are protected from one corner. So these detailed analysis you can do when you start to do when you implement technology in your cathodic protection monitoring system, right? You can do computing, real-time decision making. This is very important, right? Real-time decision making, you can analyze, and then you can make decisions on your system and improve your asset integrity. Of course, we talk about digital twin technology currently. Many companies are implementing it, where you can manage your field remotely. And this will also help. So you don't. So even as you're monitoring your valves, your pressure vessels and flows and those kind of things from the office, you can do exactly the same thing for your CP system. I know precisely what corrosion rates are you going to have on your CPC on your pipelines based on what you have implemented. Okay, of course, life cycle planning, you can plan integrated with your enterprise management. Of course, life sensor data, continuous updates, and digital twin and real-time analysis you can do. So this is perhaps where we are generally as asset technical professionals. We've not achieved everything, generally speaking, but I think we are very detailed in our processes with regards actualizing where we want to be in the future. Okay, so yeah, thanks a lot. I hope we've maybe quite a lot. Maybe we can have questions and then we can discuss again further.
Thank you so much, Engineer Gapi. So we have some few questions. Let me put them here. Can you see the screen?
Okay, yeah, okay, yes. So it says, are there any advanced pipeline integrity management methods beyond Cathodic protection being implemented in Nigeria? Well, I think generally for pipeline asset integrity management, most of the things which we need to do generally, we already know what we need to do, right? If we are doing inline inspection, if we are doing freedom of service assessment, if we are doing this one by NACE, which is alternative method to inline inspection. If you are doing Cathodic protection, internal corrosion, chemical treatment, and the likes, we already know what to do generally. I think where the gap is currently is how effective we implement. Now there are like different issues generally that happens that reduces the operator's ability to implement. From community challenges and the likes, costs is also one of those issues. But I think technology coming in now is helping a lot. For example, we are, for example, one of the systems which we also implement is the internal corrosion management system, where we are tracking chemical injections with the effectiveness of what's been injected. Right, so we're doing internal corrosion rates compared to the chemical you're injecting, so you can know if you inject more, inject less. And then this part, of course, which is for the external, for pipelines particularly, which is Cathodic protection. We already know what to do. We already know protection criteria. We already know all these things. The only thing is, okay, how effective are we implementing it? And that's where technology comes to help. Yeah.
Okay, thank you. We have some more questions.
Okay, okay. So can these latest CP systems like yours be used to calibrate and validate metal loss data from IF? Absolutely, yes, absolutely. To this sizing uncertainties, absolutely. Okay, but sizing uncertainties. Okay, for example, MFL UT methods for inline inspection. The MFL, I think it has a reliability of 80%, but accuracy, and UT has 90%. Sizing, so you could use our system to calibrate and know, particularly when you are talking about external corrosion, right? And know, okay, for these locations where we are having higher current demand, which you can know from the system, what external thickness loss are we having in that location, right? You can know. But sizing uncertainties for defects is a little bit precise, because again, your MFL tool, depending on the OEM, most times it has a 20% error margin for MFL, and then the UT has a 10% error margin. So normally, whilst you can decide, you can say, okay, for example, okay, and this perhaps a good comment to make. You can say, for this particular location on this place where we are having thickness losses, right? What potentials are we measuring from our CP system? Is it protected or is it unprotected? So for example, between your MFL or your UT picking, you probably do it maybe every 5 years or thereabouts, right? Okay, so within the first 5 years, what has been the potentials of this region, if I compare with what I'm seeing on my MFL picking ILI runs, right? So if you are seeing, okay, this perhaps a good comment to me. If you are seeing potentials which are protected, and your MFL or UT is telling you that these places you're having external corrosion, then the question is, are we having shielding effect? Is that pipeline having is the coating? Because again, this also happened over the years. We've had pipelines which we have had seemingly good potentials, but it has failed because the coating was shielding the pipeline from the current, right? So when you combine this automatic monitoring, right, with your MFL, your UT, putting your ILI runs, you perfectly understand what's happening in your system, and then you can make excellent deductive actions based on what you are seeing. Yes.
Thank you so much for the explanation. We have more questions. I think we have some time to also look at the questions. So this next one.
Okay. So once a CP monitoring survey is conducted and it is found that the structures don't meet CP criteria, what's your experience in finding external corrosion? All the time, sometimes, or not found. Okay. So generally, okay. So underprotected is below 850 standard wise, right? But there have been systems that have been below 850, but maybe like 800, 810, and then they have not had external corrosion. Remember that the minus 850 millivolts criteria is standardized across for as general. Certain locations may have certain nuances that may not require minus 850. Now, what I've noticed is that if you have a line immersed in water, wet soil, and those kind of locations, you should try your best to work with that minus 850, because when it goes below minus 800, you start to have external corrosion. It may not be serious, right, but it starts to happen, right? And of course, that's one thing to note. So the minus 850 is a criteria, but certain environments which are in dry land, arid locations, and things like that, it may not be minus 850 that is the protection criteria. It may step down to minus 750. They said the ISO standard talks about resistivity measurements for various soils and protection criteria based on over the years and tests that have been done for external corrosion. So what I find out is that for environments which are like in moist environments, moist soil and the likes, minus 850, minus 950 has been very important as to use as a criteria to make sure that you don't have external corrosion. There are even certain environment like microbial environments, right, where you have a lot of microbes, where even minus 850 does not work. You have to step up to minus 950, right? In those locations, right? This is why it's important to always monitor using remotely, because with these systems you can routinely know what is happening and know. Okay, for example, you can say this location you have minus 850, this location you have minus 950, right? But this location where you have minus 950, or rather, it's not a location where you have MIC or high temperature environment. You can step it down to minus 850, no problem. You understand? So that way you can also monitor your current demand. You can monitor how much your TRE is sending to protect your pipeline, and you can do a lot of things. So from experience, like I said, 850 it's a general criteria, but certain environments requires different or certain adjustments to that minus 850 requirements. Yeah.
Thank you. Next question.
Yes. So is there a remote monitoring solution for CIPS? Yes. This is what I was discussing about. So CIPS, like mentioned, like we understand, is just critical protection measurement across the line. So once you install your reference electrode across the entire network of your line, right, you invariably can cover your entire network to know what the potential is of your line throughout the entire network. Of course, CIPS, you are probably measuring like every 1 meter and thereabout. You may not necessarily need to have that kind of detail. You can do every 200 meters or every, typically most test posts are already at every 1 kilometer generally, right? When you have locations when you're in high risk locations, high risk zones, you can step it down to like maybe every 200 meters, every 100 meters, and the likes, and you will get absolutely a data in which you will not need to do your CIPS survey, because you already know what's happening across the entire network of the line from beginning to the end. But if you don't have, maybe if there are locations where you don't have any interference, no issues, your 1 kilometer spacing between your test posts is okay. And normally you install your remote monitoring units, you install it on every test post along the right of way. So as a minimum, you know what every 1 kilometer of your pipeline, what the potential is reading from the beginning to the end. You already know, right? Okay, but if you don't want to have more detail, you can put more test posts along the right of way, and then you can now space it and then measure. Alternatively, you don't need to put a test post. You could just need to put multiple reference electrodes, because in any case, what CIPS measures is your cable, your railing cable on your test post, and then it measures potentials along every 1 meter or 2 meters, depending on how you are doing your measurements, right? So the remote monitoring system completely replaces your CIPS, and you don't need to do CIPS surveys anymore. Manual CIPS, but manual CIPS, by the way, not like your entire CIPS, like because you're seeing the CIPS, just like it's not manual, it's now remote. Yes, so just to mention.
So I think we have time for just one more question.
Okay, so can you measure corrosion through change in metal resistance? And yes, absolutely yes. So this is very interesting. This is what we are doing. So we know corrosion rate is depending on resistance, right? Resistance of your metal to the environment, right? We know your resistance affects your potentials. Okay. If you remember, if you know how the ERP probe works, that's electrical resistance probe works, right? What it measures is that it measures the potential, right, and then it converts it to resistance of the system, and then to corrosion rate. That's exactly what it does, right? So it's exact. So currently, what we are doing, right? We have test samples, and anyway, it's not as if maybe we invented it anyway. This has been done in industry over the years, but we are just doing our own because we're trying to get some data for certain kind of calibrations. We have test samples, right, inside certain environments, which we've connected to a remote monitoring unit, right? What are we measuring? We are measuring potentials, right? Every minute or every second, right? And then after 6 months, we'll take that test sample, we'll measure the corrosion rate. What are we trying to establish? We're trying to establish at what, for these potentials over 6 months, right, what corrosion rate will happen to this material. Why I want that information is because if we know that, then we can say, if you measure this potential on your pipeline, this corrosion rate that your pipeline will be having, because it's a direct relationship, right? Potentials is voltage, resistance, and then current, right? So the normal Ohm's law, V is equals to IR, right? So this is what technology is helping us. Big data. With this, we can draw direct, clear inference and make deductive actions, and then know exactly what is happening, precise. So when you tell me tomorrow, Agape, when I measured my potential, I measured this particular voltage, right? I measured this particular metal resistance. I can say, oh, okay, based on that resistance, based on that voltage, your corrosion rate for that material is going to be XYZ, right? So this is practically what and I don't think we are the only ones doing it. I think a lot of people are doing it, right? They are doing this kind of big data analysis and using technology and technology is helping us a great deal, right? To generate equations, and this is also very important. Generate equations that directly relate these phenomenon. Yes. Okay.
Yeah, thank you so much. I don't know if we have just time for just one more question, or the person can reach out to you later. Let's just go for one more question, the last question.
Okay. Okay, so it said, can remote monitoring solution determine if anode installed in a tank are passive or depleting? Absolutely, it can. So, but it's going to determine it indirectly, right? So, for example, if we are able to measure current, if we are able to measure potentials, right? We already know that those potentials are not coming from the metal itself; they're coming from the anodes, right? So if the potential is okay, for example, let me just give you an example. Let's say we have a corrosion potential for a particular, we measure for and by the way, corrosion potential is not a big deal. It just means that a normal line which is not protected, just measure the potential with that's why the reference electrode, right? Put a cable on the line to a voltmeter, and then from the voltmeter to a reference electrode, and put the reference electrode on the environment. With that, you can measure clearly what the corrosion potential is, right? So our corrosion potential is just voltage, right? Voltage of the material. Now, if we are measuring a potential, and maybe let's say maybe it is minus 300 before we put an anode, right? And then we start an anode, we start measuring minus 750, right? We already know that anode is providing current that is protecting the material. So that's like indirect. Now, let's say we're measuring minus 950 before, right? And after like 2 years, right, we're not measuring minus 750, the same location, right? We've not changed anodes. What does that tell us? That tells us that the anode is depleting. It's not covering as much area as it was covering before. As anodes, that's how we have. That's how we have. We don't when you calculate anode requirements for a particular protection, we have like a margin called utilization factor, right? And that utilization factor, we say, okay, when it gets to 80%, it doesn't cover the entire environment which was supposed to cover before for protection. You understand? So as the anode is depleting, your potentials will be reducing, right? And then you can tell and say, hey, this anode has finished depleting because now I'm not close to maybe like minus 500 or minus whatever at certain environments. The anode may not be completely depleted, but it may have depleted to an extent where it cannot protect the entire environment to minus 850 anymore. Another one is passivation, right? If the anode is passivated, it will not deliver current. So if something happens and you see a drop, right, significant drop, or maybe you saw the anodes and you measure and you say you're not getting your protection criteria, that means that the anode is passivated, right? So it's an indirect deduction from potentials. It's not like a direct measurement of the anode itself. But when you measure it, you can know deductively and say, okay, this potential I'm measuring, the anode is not functioning well. Either it is finished depleting or it is now passivated and it's not working how it ought to work.
Okay. Thank you so much once again for this. Yeah, I think we have some more questions, but I don't think we have time for that anymore. Thank you for your wonderful presentation. Where can we reach you with our questions, if in case?
Okay.
You have more?
Well, I think just send the question to the Lagos AMPP group, and then they would, of course, be able to communicate from there. It's not a problem. Generally, I think in the industry, a lot of people are doing a lot of things, and it's good. We also communicate and also rub minds together industry-wise to know where they are developing and where we need to improve our systems. Yes.
Thank you. Thank you. Thank you. Thank you. Thank you all for joining us for this presentation. This is the final day, last day of this webinar series. It's been really fun and having all of you here, and we'll get the certificates to everyone who has attended the coming week. Thank you. Have a wonderful Sunday evening.
Yeah, thanks a lot.
Thank you.